Welcome back to Inorganic Chemistry. We're going to continue our discussion of Chapter 12, which is the reactions of coordination compounds. Last time we looked at the formation of complexes and the thermodynamics involved in the bonding of coordination compounds. In this next section, we're going to look at the kinetics and the mechanisms of how these reactions can occur, in particular ligand substitution reactions. And we'll discuss examples from octahedral or 6-coordinate complexes. In the next lecture, we'll look at square planar complexes, and we'll finish up this series of lectures looking at electron transfer reactions. Okay, so ligand substitution of coordination complexes. The idea here is that you're going to replace one ligand, which we'll call the leaving group, with another ligand, which we'll call the entering group. So by the time we're done with the reaction, we have our coordination complex again, the same coordination number, but we've replaced one ligand with a different ligand. And the other ligands present on the complex, for now, we're going to ignore. They're just filling the space, or spectator ligands. But as we'll learn, they have an important role as well in the mechanism and possibility of a ligand substitution reaction. And we've seen this ligand substitution reaction already when we looked at the formation of coordination complexes and replacing, say, a water ligand or solvent ligand with a ligand of interest. If we are replacing the leaving group with an entering group that is actually the same ligand, this is an exchange reaction or self-exchange reaction, and this actually occurs constantly. So for example, if your metal ion is in water, which we said is actually a complex of water as a ligand surrounding the metal ion, it's in water, so there are plenty of other water ligands available, water molecules available, and so this water ligand will replace this water ligand at a actually quite fast rate usually, but you wouldn't be able to observe it because the products look exactly like the reactant. So that's the self-exchange reaction. You can observe it, however, if you maybe do some kind of isotope study. And indeed, people have done these studies to look at what is the rate of the self-exchange reaction for a series of complexes. And in the case of the vanadium 2+ complex, the rate constant for the self-exchange at 25 degrees is about 69 per second. It's a I guess it's first order, so that's the units there. And so that's quite fast. And so this complex with this large of a rate constant for exchange we would call labile. It's kinetically unstable. This ligand will exchange readily. Let's look at the chromium 3+ hexaqua complex. The rate constant for this self-exchange, 4.8 times 10 to the -6 per second at 25 degrees. Is very small rate constant, therefore the reaction is very slow, and actually the half-life is in terms of years. And so we would call this a non-labile or kinetically inert complex, that this chromium 3+ is very stable. It's very hard to replace that ligand. And the cutoff here for kinetic stability, I mean, these obviously are very different values. Somewhere you draw the line and say about somewhere in here 10 to the -2 per second is the cutoff between labile and inert. Okay. And why are these complexes kinetics so different? The temperature's the same, the ligand's the same, there's no chelate, there's no multidentate ligand, the Lewis basicity is the same. Well, the Lewis acidity is a little different, right? And that is part of the trend. But we also have different electron counts. So chromium is D6, and in this case it's low spin, but we need to keep track of that. Is it low spin or high spin? And vanadium is vanadium 2 plus would be D3. So that explains some of the chemistry, and we'll look in more detail at the how the d electron count affects the kinetics. Okay, in studying these ligand substitution reactions, we've determined that there are a number of possible mechanisms, and also there's a number of possible transition states. So there's actually two ways to look at these mechanisms. One is to focus on the rate law, which we'll call the stoichiometric mechanism. Is it a first order, or is it a second order reaction? And another way to look at it is to look at the transition state or activation state, and that we'll call the intimate mechanism. So if the stoichiometric mechanism is dissociative, we lose the ligand before the entering ligand comes in. We give that a capital D symbol. If it's associative, the entering ligand binds before the leaving group goes away. We'll give that a capital A for associative. But then there's in the middle here, there's what's called an interchange, and here we don't see a transition state or an intermediate. Well, we'll go into each of these in detail. But we have two possibilities: the dissociative or associative transition state. And by definition, if we have a dissociative stoichiometric mechanism, we must be going through a dissociative transition state. If we have an associative stoichiometric mechanism, we must be going through an associative transition state. So let's look at these examples one at a time. So in the dissociative stoichiometric mechanism, or capital D, the leaving group leaves first, forming this intermediate. And then in the second step, the entering group binds to the intermediate to form the product. And usually the second step is fast, and so this first step is the rate determining step. And the reaction coordinate diagram would look like this, where we have the products, or reactants, reactants here, the octahedral complex. Then we have the intermediate with the 5-coordinate transition, or intermediate, which is obviously going to be higher energy than the reactants. And then we have the products here, which may or may not be higher energy than our reactants. And looking at the rate law, if we look at this, and work it out, the rate law should be equal to the product of the first and second rate constants and the reverse reaction of the first step Okay, so this would be the formal rate law, but it turns out we often work with large concentrations of Y, and so the Y term cancels out. This is usually slow, and so it simplifies to simplifies to a first order rate law. And so if we think back to organic chemistry, this is like a substitution reaction, nucleophilic first order. So, and that's kind of what we're doing, because our leaving group, our entering group, these are Lewis bases, which are nucleophiles, and we're substituting them, and it's first order. So very similar. You can go back and look at your organic notes to help you understand the kinetics for this type of mechanism. Now let's look at the associative reaction. And then the associative reaction, stoichiometric, so capital A, we have in our first step the formation of a 7-coordinate intermediate. Because the entering group attaches before the leaving group breaks off. So then this intermediate falls apart, either back to the starting or to our substituted product. And so again, this second step is probably going to be fast. 7-coordinate complexes are not stable, so we'd expect that to fall apart. So the first step is probably the rate determining step. And so the rate law is just this forward reaction and the concentrations of our reactants and products. And, well, that's clearly a second order reaction. So this is like substitution nucleophilic second order, as it depends on the concentrations of both reactants. Our reactant coordinate diagram looks very similar to before. We have the reactants, we have this 7-coordinate intermediate, and then we have the products. So the difference is this intermediate that's formed. And if we look at a model here, this is for octahedral complexes. Here's our X, our leaving group, and here's our spectator ligands. And this is 6-coordinate reactant. Here's our entering group. So for the entering group to bind before the leaving group leaves, it could attach here, which would create a capped octahedron, 7-coordinate geometry, which is possible. And thermodynamically, that should be stable because we have now 7 bonds, bond order of 7, so it's more bonding than it was before. But sterically, we're going to have some trouble getting this ligand to be able to fit in between these ligands to bind to the metal ion in the center of the complex. So sterically, an associative mechanism is not favorable for octahedral ligand substitution. Instead, what is favorable would be the dissociative mechanism, where this leaving group leaves first, and you can imagine, just like any chemical reaction, the bonds are moving, and you add heat, and the molecule gets enough energy to break that bond, and then the entering group can come in and bind to that open site on a 5-coordinate square pyramid. So, kind of like SN1, it looks like the geometry doesn't change when we do this dissociative reaction. But as we'll see later, the square pyramid is not the only geometry for a 5-coordinate ligand, and it could shift here in the intermediate state before the entering ligand arrives. On the other hand, when we look at the associative mechanism, then kind of like SN2, we're going to get some change in the geometry because this is going to have to shift. These bonds are too small. They're going to have to shift down when we lose that leaving group, shift down to form the new octahedron. And so that's going to change the geometry around the metal center in an associative reaction. Okay, well, we don't always see an intermediate. And this leads to the stoichiometric reaction we call the interchanger, capital I. So we have reactants, they form products, we don't see an intermediate. Clearly though, there's going to be a transition state, a high energy state intermediate in between reactants and products, because the reaction has to proceed somehow. And so we could think of some kind of maybe ionically attracted, so it's not chemically bonded here, but it's a dipole attraction here in the transition state that eventually falls apart to form the products. And it turns out under most reaction conditions, this is a pseudo first order reaction. So we can't tell just from the order of the kinetics rate law whether we have an interchange or a dissociative reaction. And again, the key is that there's no intermediate formed, or at least detected. So what distinguishes the types of interchange reactions? You could have either an associative transition state or a dissociative transition state. So in the associative transition state, metal forming is going to precede bond breaking, bond forming. So this part, where this bond is being formed, is more important energetically for the transition state. And so that would be an associative type mechanism. And that's showing how important this bond forming is given with the solid line. If bond breaking is more important, so this entering ligand is coming in, but it hasn't quite made it, right? It's forming this pre-bonded, maybe ionically attracted complex, but in the transition state we have to break this bond first. This is the most important contribution to the formation of the transition state, and so that would be a dissociative type mechanism there, and in the transition or activation. Okay, and so there's a lot of evidence for these types of mechanisms. We did say the rate law alone isn't that helpful, but we can look at other factors, like we looked at the sterics. We can also look at the electronics. So let's look at what happens when we form this square pyramid transition state. So if we have an octahedron reactant, square pyramid intermediate, and an octahedron product, or square pyramidal transition state, we can look at how the electronics are going to affect the energies, and we'll do that by looking at what's called ligand field activation energy. So going back here to our reaction coordinate diagram, remember we have this energy of activation, and what contributes to the energy of activation is bonds having to stretch, bond angles having to bend, and electrons having to move. So if we look at our electron configuration and the octahedral splitting, we have the 2 ligands up, 2 ligands down. I'm going to try to spread that out a little bit more there. In the square pyramid, we lost one of those coordinates, and so that decreases in energy one of the top 2, and the bottom 3 actually shift a little bit as well, although not very much. So this is the ligand field splitting we'd expect for a square pyramid. And so we could calculate what is the ligand field activation energy by taking what is the ligand field stabilization energy of the transition state minus the ligand field stabilization energy of the reactant. That will tell us how much electronic energy was required to reach this transition state. So let's look, for example, at a D6 low spin complex like chromium 3 plus hexaquo, which we saw was unusually stable. And so we put in our electrons, 1, 2, 3, 4, 5, 6. So the ligand field stabilization energy of the reactant we can calculate is negative 2.4 delta octahedral. And the transition state, we have 1, 2, 3, 4, 5, 6 electrons. Again, in the low spin, the low orbitals are filled. So you can calculate the ligand field stabilization energy for that as negative 1.828 delta octahedrons. So the total ligand field activation energy is positive 0.572 delta octahedrons. So this is positive energy being added here to our energy of activation, so that transition state is higher in energy due to the ligand field splitting for a D6 low spin complex. And so that explains why the chromium 3 plus D6 low spin is kinetically inert. At least partly explains it. Other factors that contribute to the reaction mechanism are actually going back to the thermodynamics. So here's again our reaction coordinate diagram and our energy here. So our reactants, transition state, products. And we already labeled here the energy of activation is here. And this part here we didn't label yet, but you should recall this is our change in enthalpy. This is our thermodynamics. And not always, but sometimes the thermodynamics will influence kinetics. So back in Gen Chem, we taught you about thermodynamics, we taught you about kinetics, and we said they're separate. Here we see that actually they're related by what are called linear free energy relationships, which says that if we change the free energy, I'm showing enthalpy, but delta G I could do as well. If I change the energy here, that can change the height of this energy of activation. If I lower this, for example, then all things being equal, this line will have to lower down as well. So my energy of activation would decrease. There, let me try that. I went so low I went off the graph. And that was increasing the delta H, decreased the energy of activation. This isn't always true, but it does show up in some of the data. So for example, we could do this substitution where water substitutes for this anion. So we could call this hydrolysis, the water's breaking up the complex, or aquation, because we're adding an aqua ligand. And for this particular complex, cobalt-3 complex, the rate of the substitution The reaction rate goes with this trend if we have these different anions here. So the hydroxide substitution, or the substitution of water for the hydroxide, is slower, for example, than the substitution of chloride as the leaving group. So this is slower, which means it's more kinetically stable or more kinetically inert, which also follows the trends of thermodynamics. This is also the strongest base in this series. So, or it's the best ligand. So this tells us if this cobalt ligand bond is strong, then it's slower for this reaction to proceed. And that's the same thing as saying that we had to, if we have to break this bond, it's going to take more energy to get through the transition state. So the thermodynamics of this metal ligand bond affected the energy of activation and affected the kinetics. And actually then, because this experimental evidence, we know that this is going through a dissociative mechanism. Or at least it suggests that, because if breaking this bond is what is slowing down the reaction, then we could theorize that that's the first step, the slowest step in the reaction mechanism, and we go back and look at our options. That is indeed what happens here. We have to break this bond first before we can proceed with the reaction. That is the dissociative mechanism, and that's what this data then suggests for this complex. So thank you for your attention, and this concludes our looking at octahedral ligand substitutions. Next we'll look at the octahedral, or the ligand substitutions for square planar complexes.